All right, let me come back and do the example of the sweep meshing again. So that was the other type of boundary condition that I was interested in. So in class, I showed an example of how to do this. I'm just going to go back and revisit the exact same example that I did. So in class, I did an example, and this was sort of the final mesh that I was looking to make. So like the sweep mesh refers to how it takes, like it generates some mesh on the surface of one face here, and then it just basically propagates or extrudes that mesh in the through plane thickness. And in this case, I asked it to make 6 of those. So I did that on a bunch of faces. Like you can see, like that happened here, 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 and I had also done it on the bottom here. So let me go back and show you how I did that again. And in fact, I'm going to make another. Like typically when you do the reason why you do multiple meshes, like in your assignments, will be, a lot of times you want to create multiple meshes with different numbers of elements, but in a systematic way so that you can test whether you have enough elements to get an accurate answer. So I'm going to do a case. You can see this one has like 6 layers through the thickness here. I'm going to go back and redo this, and I'm going to make all of the elements in this entire simulation twice as big. So that means instead of 6 in the through plane, I'll have 3, and whatever like distance I was using for the size of these elements in whatever this direction is, I'm going to like double that so that our elements are a lot bigger. So I'm going to do that everywhere. So I'm just going to go back and create a new mesh. So like when you go to start your new mesh, you'll come back to this blank part again. So there's no meshes here, and I'll have to specify what that is. So again, like I don't really recommend using this slider for fineness, so the default sizing in SimScale, because I have no idea how it like decides numerically how to make the element sizes. So I'm going to switch that to manual. I think what I said like when I did the simulations last time, I think what I did was I had made a maximum element size of 1 millimeter. So I'm going to make that twice as large this time. I believe that's right. I'll go back and double check in a second. But actually, let me do that now. So I'll go back and check our first mesh. Yeah, so for the first mesh, I made this number 1 millimeter. So in my second mesh, I'm going to make that twice as big, 2 millimeters. In this case, I don't believe there are a lot of small features to suppress. So meaning that like if I really zoom in here, I believe that there's not a small gap here between like this edge and where this fin starts or anything weird like that. So I am going to I can probably reduce this, but I don't see any small geometric features that are ruining this model. So I'm not really going to play with this. I'm going to be defining, there are a lot of small gaps in this model, like each one of these is a gap, but I'm going to be manually meshing each of these. I'm going to be specifying the sweep mesh, so I don't really care what that is set to here. I also know from my previous mesh that, by the way, the gap refinement factor referred to the number of elements across a gap. So like the gap refinement factor, if I set it to 4, means that I want the maximum element length to be about 1/4 the thickness. Similarly, the global gradation rate is a measure of how big an adjacent element is allowed to be, like compared to a different element. So like if I want the adjacent element to not grow by more than 22%, I would set this to 1.22, which is the default. I don't know what a good size is. I generally use one that's a little smaller than this. In this, honestly, in this example, it doesn't matter because there's not really a lot of inflation in the element sizes. Okay, the big thing is the refinements. So there's lots of different ways to set refinements, right? So region refinement, like I could set the maximum element size or the minimum element size for a certain volume. A local element size allows me to set the maximum element size on a face, of a solid. The one that I'm going to use now is the sweep meshing refinement, which allows you to take a surface mesh on one face and propagate it through to the backside of that face. So I'm going to do that for a bunch of very similar faces. So like there's this face. I'm going to want to do that for this fin, this fin, this fin, this fin, and this fin. I'm also going to want to do that for my bottom solid here. I could probably do it for this top solid too. I didn't even think to do that last time, but I'm going to do it the same way I did it last time. I'm not going to worry about what happens in here. I don't really think that those elements are very important. Let's see. So I'm going to set it up so like there's different ways I could choose like how thick I want each element to be. But in this case, I just want to specify the number of elements. I know that I said that I would have like 6 elements last time, so this time I'm going to use 3. 3 is like sort of the bare minimum if you're trying to model a fin, by the way, because like the temperature inside of a fin has an inflection point at the center of the fin, right? So like as like the temperature on each wall is lower than at the center line ever so slightly. So if I want to capture that, I really feel like I should have, like 3 to capture a parabola. So I'll leave it at 3, which is half as many as I had. So that's going to basically cut our size scales in half compared to the last mesh. I think it doesn't really matter, but for the surface meshing portion, previously I had chosen quad elements. So I'm going to do that again. And, yeah, you can specify, like if you think that things should shrink from the beginning to the end, you can do some extra calls, but I'm not going to do that. And then I need to assign so these were all the starting faces of the sweep. Now I need to select this red region, which is like allows me to specify the end faces. I'm actually not sure whether you have to specify these in the same order that they were specified above. But I will, because my gut instinct is that probably helps the solver do this more quickly. So I'll do it in exactly the same order that I had selected the front faces. So this one, then 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 this one. And then similar, so in class I had this same problem. So the face for this one is actually hidden by this other solid that's up here. So you actually have to hide that solid. To do that, you can right click. It'll bring up a bunch of stuff. So you can, so if you hide SS base is the name of this solid. I had named it in the CAD editor. So I can hide it, hide the entire solid. Now, there is another option here that's kind of interesting. So you can hide the face. So like this face right here, I can hide that face. That's actually a bad idea because if I hide the face, the other faces of that solid still exist. And since there are actually 2 faces that touch each other at this interface, I actually don't know what face I would be clicking on if I were to click there. So I am going to hide the entire solid by clicking hide SS base. And now when I select my end face, I will select the top portion. And then if I want to bring back that solid that I had hidden, I can right click again and I can click show all. I believe there's another way to do that. So over, you click show all. Also over on the right hand side where the geometry is, it'll say what's hidden. So you can click the little I button to bring it back. And now everything is selected. So, boop. So now we've got all of our stuff. And basically, like if I look at how I defined these mesh refinements, so because I changed this from like 6 in the original mesh to 3, that's going to cut the size of each element by 2. And then similarly up here in this mesh area, I am doubling the mesh length. So basically, I'm going to increase all length scales by a factor of 2 when I do this. So that being said, I'm going to generate this. and then I'm going to wait patiently and restart this video once it actually finishes. All right, it looks like my mesh has finished being made, and now if I look at it, it is exactly what I asked for, right? So it's got 3 meshes deep, or it's 3 elements deep along the extrusion. And if I look at sort of the size of these blocks, they're a lot bigger than the previous mesh. So they look like they're probably about, well, they're not actually 2 millimeters long. For whatever reason, they're more like 1 millimeter long here. But anyway, doesn't always do what you ask for. Those were maximums, not minimums. It's weird. It really did make them all like one. Looks like it made them all 1 millimeter, even though I said the maximum edge length could be 2. Now, if I go back and compare it to the other mesh, though, so like, boop, if I go back and look at our original mesh, similar thing, right? Like, it had made these things like almost twice as small as I had said the maximum was. So, and then like our previous mesh obviously had like 6 elements deep. So let's see. So if I change the x dimension of like an element by a factor of 2, and I change the y, what would I say? The y and the z direction by a factor of 2, then that means that each element grew by an average of 8-fold, which means that I should have 8-fold less elements. So if I take a look, mesh 1, so the one I generated in class, had like 1 million nodes. And this one's got about 130,000 nodes. So this mesh is far less dense. So like if you were like looking to do a comparison for validation purposes, these would be a good set of like to compare against. Now I don't think that having 3 elements across is probably not going to lead to like the most accurate set of results, but it can at least help you come up with an error bar. For example.